Yeah, hello everyone. My name is Tasneem. I'm the senior manager at 98 Percentile in the HR department. And today we did a wonderful drive with XLR. It was amazing right from the very beginning, from the very first day when I got in touch with them till today. I think it was an extremely smooth journey with them. There were multiple follow-ups done by the representatives in order to check that we would be, what time we would be coming, how many people would be coming, what vehicle we would get. To that extent, they were so precise in giving all the information to us. It was extremely great to get associated with them and have a drive at XLR campus. So we are very, very happy that we got a chance to do this. Now, coming to the students, what XLR had, I think they were extremely enthusiastic. They were well prepared. They were aware of what they are coming for. I think there was some back-end preparation which they did that was commendable. They also were very confident and they were open to any kind of thing we were asking them to do. That was I think the best part. Now, I really hope we have a very, very fruitful association with each one of them and XLR in future. We are really looking forward to have many more drives like this.
Hi everyone, my name is Prachi Sharma and I'm the Senior Project Manager for IT Department at 90th Percentile. So today we were here for this IT Bootcamp, right, this technical drive and at XLR. So it was a great experience and I would feel that the students, they are the freshers, right, but it doesn't seem like that. So if I talk about their technical and cognitive ability, they all seems pretty good in that and that's what I felt. And I guess they have been taught pretty well at XLR, so that's how they have performed good in their aptitude and the technical tests. So I wish them all the best, and it was a very great experience over here.
Hi, this is Patan, Technology Consulting Manager from 98th Percentile. We visited XLR for the campus placement drive and it went very well today. Ms. Ambika, Ms. Pragati, everyone received us greatly here and we had a lot of enjoyable time here. The students even had great experience with us they were interactive, they had good aptitude, and all the technological skills they showed. I think they were all well, and we really appreciate their time that they spared to us, and I think we will be doing a great job. We are expecting a lot of people to be hired from them. Let's see. It was
into the cyber tower to exiting out of this tower. The XLR team has been received me with such a care and pleasure.
I am the part of this XLR since 4 months. From the third month itself, they have conducted the placement sessions from the third month itself, and this is the fourth month, and this is the 90th percentile is one of the placement drive I have attended so far, and attending to this drive is such a good experience for me. All the HRs and the team made us feel very comfortable and confident.
XLR helped me a lot, and I experienced a lot of things today. So I'm really hope to be I placed in that company. I'm confident about that. Thank you.
Okay. So, hi everyone. So, from past couple of days, we were discussing all the Hadoop ecosystem related tools, and we have covered uh, Hadoop installation on day one. Then day two, we discuss various components in HDFS or in Hadoop ecosystem. And in that, we have covered scope, MapReduce first, and in MapReduce we discuss what is how we write a MapReduce job and what are the various limitations we have in MapReduce. So we discuss that the language constraint, file format issue, batch processing, and also it process data into disk that is slow, that is comparatively slow than other ETL tool nowadays like Spark and Spark, Storm, and other tools. Then on day three, we have discussed Scoop, that is a data ingestion tool. And now today, I will start with Hive. So you can say it's a uh, transformation tool or analytical tool on top of HDFS. Now, so see this architecture. So here our source system is MySQL and our target is HDFS, that is data lake. And now from source to target, I want to ingest data, and we have multiple sources and this data is huge, so we need some sort of parallel processing tool that will ingest data in a faster manner. So Scoop is that option. MapReduce is the first option, but again I said MapReduce is, because of the limitations, we are not using MapReduce here. So now here we have Scoop. So in Scoop, we are directly dumping into HDFS. It's just a plain ingestion. We are not analyzing that data once it's stored in the target. So now this option two is the good option that ingest data in Hive table. And Hive is a virtual space or virtual tool on top of HDFS. So it store data in HDFS only. And also it stores its metadata in RDBMS source like MySQL, Oracle. And now we pass through data, passing our data through Hive table, so we can query the data that is stored in HDFS. So let's see the practical implementation of this. So first we need to connect with the server. So this is a server, and here I have HDFS, Scoop, Hive, all servers are available here. So just check the IP. So this is my IP. Let's connect. 92.168.1.48. Now it's connected. So password is Cloudera. Username password is Cloudera only. Now first start your source system. So source is MySQL and password is Cloudera only. Now use database MySQL, and here we have all the tables. Now start one more shell, and that is your Hive shell. So what happened? Oh. Login is Cloudera. Password is Cloudera. And start Hive shell. So it will start Hive shell where we can write our Hive queries. Mhm. Is happening. Start one more session. Cloudera. And password is Cloudera. And here check any other service. Yeah, now it's triggered. Hmm. So in the meantime, the shell is starting. So let's discuss this. So, hmm. So Hive is, as I said, it's a analytical tool. Okay, so it's kind of a relational database on top of HDFS. And as we can see here, saying it store data in RDBMS sources, and its actual data is stored in HDFS. It's not used for transactions. It's only used for analytical operations, bulk read and bulk write, not for update or deletes, not for transactions. Okay. So we have this architecture. So here we can see right now we are using Hive services because we set up our data lake environment. And when we set up the data lake environment, most of the time getting so it's because you are uh, adding wrong password, maybe some internet issues. That's the only reason. Okay. So let's see will this started or not. Stuck. So let me restart Cloudera. Otherwise, it will take a lot of time. Power of the machine and restart Cloudera. So your Cloudera is restarted. So in the meantime, we can look the architecture. So here, these are Hive services. So right now, data lake environment, we are owning data lake environment. So that's why Hive CLI, Hive server, and this Hive web interface, it's accessible to us because we are owning the Hive environment. And if, let's say, data lake is setup is in one organization and another organization is filing the queries. So in the client, let's say some other organization, they want to interact with Hive. So they will use these clients, JDBC client, Thrift client. So using these clients, they will connect and communicate with Hive. But as of now, as we are owning the environment, so we will use these interfaces to interact with Hive. Main is the driver. So whenever we are sending any request, that request is handled by driver only, and driver store the data in the file system, and its metadata is stored here in the metadata base. An execution engine is used for the processing. After processing, it store the data, or it will pull out the data for analytical purpose. Okay, so um, also if we see the detailed architecture of Hive, so here we can see this is the UI. I will show you the practicals, but let's see the architecture, how what all components are available and how they interact with each other. So we are sending the query from the UI or through web interface or through CLI, and that query goes to the driver. Now driver fetch a query plan from the Hive compiler, and it retrieves the metadata from RDBMS source. As I said, its metadata is stored in Hive. So it retrieves that metadata information from RDBMS, send that metadata to the compiler send that information to the driver, and then driver send that planner information to the execution engine that execute the actual job on the HDFS cluster. So Hive job is also converted into MapReduce. It's a wrapper on top of HDFS. Okay. So after processing, then it gives the result back to the driver, and driver fetch the result and send back to the user who requested. So these are the various components that is used within the Hive engine. Okay, so let's wait for this to start, and then I will execute the commands. So first we will load data. We'll create table. So in order to load data in Hive, so Hive is just like database only. So let's see this. So suppose you have, as I said, we can access using web interface or CLI or using JDBC if we are connecting externally. Okay, so it has database, table, row, column, similar to a database only. So let me. So this is my data set. Okay, so in my data set, there are three columns. There are three columns in our data. So first the username, then the post, and third is the timestamp. So now let's suppose this data is huge and we are storing this data into HDFS directly. So if we dump this data directly into HDFS, it is of no use. We're not able to query. But now we will store this data in Hive. And then if we store this data in Hive, that will be dumped into HDFS automatically, because Hive warehouse is HDFS only. So in order to store data in Hive table, so first we need to create our schema. So just like SQL databases, so create table name, the username, post, time. So our data is comma separated. So that's why we are giving delimiter as comma. Stored as text file. So text file means the raw format. So whatever format our source file have will store the data in the same format. So once this table is created, then we can show the table, we can describe, and then using load command, we can load the data. There is no insert here. We use load. So load data from local into the table. Okay, so let me execute this. Yeah, so it started. Go to Hadoop user interface. In the meantime, connect with Putty. It's starting the services. So our IP is this. This is the IP. Okay, that's connected. Now start the it's still starting the services. Oh, check with the Adobe file system -ls. It's started. There's something wrong. It's services is not started. Yeah, that's like running, but mm, no to host. Due to some reason, the services is not starting. Is running. I shall. I will also. That's not able to connect with HDFS. Actually, HDFS is not running. Let me start this. Okay, so I just restarted this again. So let's continue on the theory part. Once it is up, then I will execute. So we have, as I said, so when we have the data, so don't dump this data in HDFS directly. Always store this data in Hive so that we can query the data after it is loaded in HDFS. Okay, and this is the way to load the data. So first we need to create table, and then using load command will load our data set into Hive table. Okay, so the querying data, it's same, some simple select queries. So we can do a count, but here in the logs we can see if we run these queries, so they are converted into MapReduce only. So yesterday we see in case of Scoop job is also converted into MapReduce. So in a similar manner, uh, your Hive job is also converted into MapReduce, and you can write simple select queries, read operations. Okay, you can drop the table, and this external table concept I will explain later. Now we have discussed this architecture that it has a driver, and driver handles all the requests that comes through the client. So using CLI or GUI, whatever interface we are using, so we can send the request that is handled by driver only, and then driver store the data in Hadoop and store the data in metadata in a RDBMS source. Okay, so as I said, the components of Hive. So in Hive, we have a meta store. So meta store is the data about data. So um, the what is the table name, when the table is created, the type of the table, whether it's an internal table or external table, what is the data retention period. So these sort of information is stored in Metastore. Okay. So execution engine execution, as I said, by default, MapReduce is internally it uses MapReduce only. We are just writing SQL queries, that is a wrapper. So those SQL are auto converted into MapReduce only. Okay. Now services wise, as I said, we can access Hive using CLI, and then we can access using web interface. Okay. And there is also one more, you can say it's a JDBC based client. So it's for the external users. So Beeline, CLine also we can use. So here it's showing how this system interacts. So these are the web interfaces, and this is Hive. Here it has Metastore, and this is Hive driver that interacts with HDFS to store the data or to pull data from the Hadoop. And this is web interface. This is CLI. We also have Thrift API, Thrift server to interact with the Hive driver. And this is the complete. It's showing the complete picture how this communication happens. So Hive is doesn't store the data. It's store the it's a virtual storage. It's actual data is stored in HDFS only. So and if I talk about Metastore, so metadata I already discussed that metadata is the data about data. So metadata is of three types. You have embedded metastore, local metastore, and remote metastore. So in embedded metastore, data is stored in a memory database. The cache, Derby is a memory database. So it's not feasible if we submit multiple jobs on the cluster. Okay. Now, if we are submitting multiple jobs, this RDBMS sources like MySQL, Postgre, DB2 is feasible. Now, remote. So here we can see this meta store is stored in the same instance where Hive driver is installed. But here we store metadata outside of Hive, that is remote meta store. So mainly the second and third option we normally use in real-time environments. So let me check. It started now. Yeah, it looks like it's working now. Okay, so let's connect. Let's connect to this machine first. So using this command. So connect to the server. 168.1. 28. Now login is Cloudera. Now start MySQL. Password is Cloudera. Now use MySQL and show databases. So these all are the databases available. Okay. By default, Hive metadata. Metadata is stored in Metastore. This is the database. So use Metastore. And now see the tables inside this Metastore. Now these all are the meta tables, Hive meta tables. And these tables are provided by Hive only. And here we store the metadata information. So let's process some data. So start Hive shell. Hive shell. So Hive shell is starting. Okay, now show tables to check the tables in Hive. So these are the tables available. Okay, so let's create this table. Where is the table? This is my data set. This one. And this is my table. So first create the data. So I have already created this data set. So this is user post.txt. Where is user? This one. This is my data set. This is the text file. Okay. It's on my local only. Now I want to store in HDFS, but I will load into Hive only so that I can analyze this data. So we need to create tables. So copy this. So create table post. Post 500. And these are the data types. So Hive also uses the similar data types. So if I show you the data types, so the standard data types, int, float, string, date, and these are standard data types. This is used for nested data set. So I'll explain later how we store nested data set in Hive. So let's execute this query. The table is created using this command, describe post. Okay, now load the data into this table. So load data. My data is on local and it's on desktop only. So home, Cloudera, desktop, and the file name is user post.txt. Yeah, this is fine. Okay. Now, and what is the table name? Post 500. So we are loading data from local into Hive table. Okay, now it's loaded. Select start from post 500. Yes, you can see the data, but this data is not actually loaded into Hive. This data is in HDFS only. So first first check the where is actually stored in HDFS. So go to HDFS. Now inside HDFS, there's a warehouse directory. So as the installation time, where Hadoop is installed, Hive is installed, so we define a warehouse directory. It's a fixed directory within HDFS where all the Hive data is stored. So this is the warehouse directory, and here we can see this is my table, and then here is my data. Okay, your data is here only. Now see that metadata. So metadata is stored in here. These are the meta tables. So this is the table TBLS. So if I search star from TBLS, so this is the Hive meta table. It will provide us the information. So here we can see the last row. This is our meta information regarding this table. So if I write describe TBLS, so here the table ID, creation time, the retention, who is the owner, table type. Here it's showing manage table. Manage table is called internal table. So whenever we are creating table in Hive, that table is a internal table. We can create external table as well in Hive. I will explain that later. Okay. So now this shows that Hive data is stored in HDFS and its metadata is stored in some RDBMS source. And this, the query, the data that we are querying right now, actually this query is fired on HDFS only. So from HDFS, it's pull out the data and then it converted that into table and then present us the result. Okay, it's not the physical storage. So let's see more examples. So now we are loading big data into HDFS. Now, if we directly dump data, that is not a good practice. We need to use some optimization techniques before loading data into Hive tables. So let's discuss those optimization techniques one by one. So in Hive, we have Hive optimization techniques. And in optimization technique, first technique is partitioning. Now, create partition table. So partitioning is of two types, static partitioning and dynamic partitioning. Then another next optimization technique is bucketing. Then we can use joins, Hive joins. So in joins, we have map join, bucket map join, SMB join, sorted bucket map join. And then we can use indexing. Okay. And yeah, these are the only techniques. So based on our requirement, we can use. So let's start with partitioning first. So let me show the data. So these all are HQL scripts. So I will share these scripts. Here I've created all the commands within the script only. So let's see this example. So this is my data set. Okay. Here we have this first row, the first name, last name, address, country. These all are the columns. Now let's assume this data is huge. It's in billions or trillions. And now I want to filter out the users from country India. So let's suppose this data is 10 million and India data is 2 million. So it will scan the whole data. It will scan the full table and then it will filter out the result. So it will take so much time to pull out this heavy data. It's not a good practice. Your Hive query will be slow. So we can create country-wise partitions so that it can filter that particular partition only. That's the main objective, so that your data scan is limited. And if data scan is reduced, so you can, your query will be fast. That's the main objective behind partitioning. Let me explain with one more example. Oh, okay, no issues. So let's implement this. Where is dynamic partition? So open the script. So in order to implement dynamic partition, please post my attendance. Amar will take care. Amar is on call. So let's say this is a Hive server, and here we need to create Hive dynamic partition table, and create a temp table as well. Now your data set is here. Let's say as text file or a CSV file, whatever. Now, let's first load this data into temp table, and then from the temp table, load data into dynamic partition table. Okay, so that's how we'll write our script. So here, create a temp table. So we have all these columns based on our data set. These are the columns. You can see the column headers. It has first name, last name, address, country, city, state. Now, the table name and then the column names. And data is comma separated. So this table is created. Now load data into the temp table using load command. Then next we create partition table. So how we create partition table? We pass the columns that we pass in filter clause. So let's say select some table name where country equals to US. So country is the filter column. We pass those filter column into partition by function. So here we are creating partition based on country and states. So if let's say country India and partition Haryana is the state, India, Delhi, India, Karnataka, Andhra Pradesh. So that's how we can create these partitions. Now insert data into partition table from temp table. Okay. So let me execute this script on the server and see how it creates the partitions internally, and check whether this table is, so partition table is here. Let's dot this table first. Dot table this. Now table is dot. Now we can execute the HQL script on this Hive server. So open one more shell. And here on desktop we have the scripts. File scripts and dynamic.hql. Here is my script. So Hive, this is how we submit a Hive script. Hive -f and this dynamic.hql. So now the script is submitted on the server and it will execute the commands. So this the temp table creation and then loading of data into temp table and then partition table creation and then inserting data from temp table into partition table. So here we can see your job is converted into MapReduce. So as I said, everything is converted into MapReduce only. Okay, so right now this job is run. We're creating partitions. So in the logs we can see these are the partition names. So in the meta database, we will see how many partitions are created, what are the partition name. So that metadata information we can collect from meta server. So now it's completed. And now go and check how many partitions are created in HDFS and what is the size of the partition count. So go to metadata table. The metadata is stored here. So this is the row, the last row. So this is my table ID. And now this table ID is connected to the another table as a foreign key into this partition table. So this is the partition metadata table. In this table, we can see the actual number of partitions that is created. So select star from partition table, the partition table, this table. Where table ID, where table ID equals to 57. So we can see total 168 partitions. And these are the partition name. So US, California, US, North Virginia. So here it's showing the country and state pair. Total 168 partitions are created based on this data. Now check the actual partition, the actual data in HDFS. So here in warehouse, we will have the actual data. So this is my partition table. And this is countries US, state is California. And inside this, we have this is the data. So this partition holds data for this country state pair. Now the another partition holds data for another country state pair. Okay. The US and any other region. So Illinois. So this partition holds data for US and Illinois state. So now this partition data is created. Now if we query the data, it will be fast. So select star from this partition table where country US and state equals to California. So it will filter out, see how fast it is. Takes hardly 1 second and fetch these 72 rows. If this table is not partitioned, so it will scan all the data from the table and then only filter out the records. So it will slow down the query. So when we have huge data, then we do the partition so that data scan is limited if we are querying the data. Any question on this? Whatever I have implemented so far. Hello. Hello. Any question? So this is how we implement partition. So as I said, these are optimization techniques. Okay. So we have partition, bucketing, and this joins, indexing. So all these are optimization techniques that we have used. So partition, uh, again, your query scan is limited if we implement partitioning. So we need to use these techniques when we are storing the big data in HDFS. So if we implement these optimization techniques, so your data scan is limited and your query performance will be faster. So now let's see static partitioning now. So one more thing we need to notice that these two properties on top. So we need to set these properties because these configuration are not enabled by default. We enable this configuration based on our uses. Okay, so let's set this property. So when we execute this script on the server, that time this is auto, you can say these properties are automatically set. But when we are implementing things on the Hive server or in the session or a Hive shell, so we need to explicitly set these properties. So first we set Hive dynamic partition true, and the next property is non-strict. So strict mode is your static mode, static partition, and non-strict mode is dynamic partition. So static partition is enabled by default. Dynamic partition we need to enable. So in order to enable this, we set this property non-strict. Now dynamic partition is enabled. Now we can implement dynamic partition. Now next is static partitioning. Now in case of static partition is a you can say manual creation of partition. So in case of static partition, we will not create any temp table. We directly load data into the static table. So we need to create our Hive static table and load data directly into the Hive static table. So let me show you how we create static partition. So here we can see we have created this partition table. So we are creating partition based on country and state, and now we are loading data into this table. So here we before loading in the source data, manually we detect the unique country and state pairs. So we need to be aware, okay, so these are the unique country and state pairs, and these partitions we need to create. So manually we need to execute this load command 168 times because there are 168 country state pairs. In case of dynamic partition, it will automatically detect the unique partition columns, and it will create columns and start loading the data. In case of static, we need to manually create this. So let me execute this command. Where is the local path? First check the script local using cat command. So your data path is this. This is not correct. First we need to change the data path. Go to Hive scripts. Where is Hive script? This one. And here, where is local path? And here, home, Cloudera, desktop. And on desktop, Hive scripts. Hive scripts. And inside Hive scripts, there is the data. Data is yes. So this path is correct. Save this and now execute this. So in place of dynamic, we can write this script name. Hive local path or HQL. So this is how we submit a script. So now we have submitted the static partitioning script on the Hive server. So it will create one partition only. So next time, if we now this is what happened already exist. So change the partition, change the table name. So just write static underscore partition into table static underscore partition. Now execute again. Now it's executed and it's done. So verify the table, check the metadata first. So this is a static partition table and see how many partitions are there. There will be one partition only. So table ID is 58. So you can see there's one partition only and you can check the actual data inside warehouse. So this is the static partition and this is the first country state pairs. It holds data for this partition only. Okay. Now, next concept is bucketing. So, what is bucketing? Let me see this example. So, let's say we have departments, HR, account, sales, IT, marketing. So, when there's a uniqueness in the data, there's more data uniqueness, go for bucketing. If there's less data uniqueness, then go for partition. And we also create same table as partition and a bucketing table. Okay, so here we can see there are 3 departments, and now inside department we create buckets based on the salary column. So bucket is like a container. Okay, so and also we can decide how many number of buckets we want to create within a partition. So here it's showing 2 buckets only because we defined buckets as 2. So the employees having salary 10,000, 20,000, 40,000 is stored in one bucket, and the employees having salary between 30 to 50 is stored in another bucket. And next time when data arrives, so it will check whether employee having salary between this range, it will go to this bucket only. And same partition key data will reside in the same bucket. Okay, so let's implement this. So in case of previous example, country and state, we can create partition based on country, and we can create buckets on states only. So let's see that example. So here in this example, we can see, so first we need to enable these 2 properties, that is static, dynamic partition because it's static partition is enabled by default. Dynamic partition we need to enable. Now, second is for the bucketing because right now we are implementing bucketing, so we need to enable bucketing as well. Now, same uh, in case of dynamic partition, first what we did, we create the temp table first, and then we load data into the partition table. So same thing we need to implement. First create a temp table. Okay, this is our temp table. Now load data into the temp table. And then this is my partition and a bucket table. Both partition and bucketing is implemented within the same table. So we can create a separate partition table. We can create a separate bucketing table, or in the same table, we can implement both. So here we are creating partition based on country, and clustered by is for buckets. Okay. And we are doing bucketing based on state. So, and how many buckets we are creating in a partition? We are creating 4 buckets in the partition. So it's on us how many buckets we want to create per partition. Okay. So now let's say in India we have 30 states. Okay. And suppose 5 states data I want to store in 1 bucket. So we will provide 5 buckets. So we will have total 6 bucket, and in 6 buckets, every bucket is holding data for 5 states. If I provide, let's say 4 buckets, so 4 buckets means 6 states data will be holding or stored in 1 bucket. The next bucket holds next 6 states data. So that's how this data stored. And if you run the query and you see that there's a performance impact, we can further increase the bucket so that our data reduces within a bucket. Okay. And bucket uses hashing algorithm. So with the hashing, your data retrieval is fast. Okay. So bucket, if you're storing data in a partition and a bucketing table, bucket is fast because it has internally it using this hashing algorithm. Now, once this bucket and partition table is created, now we can insert the data into this bucket table. So let's implement this. So here is my shell ls, and where is the bucket script? So say the hive, and here we have this hive bucket HQL. First check that proper path is provided. So the data path is fine. Now let's execute. Before that, just check whether this table, if this table is there, it will throw exception that this table already exists. So show tables. Show tables. Yeah, this table is there. So first drop this table. This table is dropped. Now we can execute the bucket script. So hive reference and the path of the HQL script. Now it's executing on the hive sub. So this script will create the partition and a bucketing table. And when data is loaded into this table, it will first create partition and then store data in the buckets that is created within a partition. So now it launched the mapper and trying to create partitions, and we can see the this script is converted into MapReduce only. Still executing. Okay, so now it's loaded the data. So first verify the metadata. So metadata is stored here. So this last row, this is the meta information, and this table ID is 59. So check how many partitions are created. So in total, we have 6 partitions. Okay, these are the partition names. And now check the actual data that resides in HDFS. So this is the warehouse, and here this data is actually stored. And this is country, and these are states. Okay, so bucket is actually a file. Partition is a directory only. So, and now this data is encrypted using those hash codes. So that is because, as I said, bucket uses hashing algorithm internally. So if we execute the query, select from bucket table. Let's check the table. Now this is the table, bucket user, where country US, and state California. So you can see how fast it is, 0.17 second. So it's because of partition and bucket pairs. So that is the biggest advantage of using this partition and bucketing, that your data retrieval is fast. And when we are dealing with big data, we need to make sure that our data ingestion or data retrieval, bulk ingestion or bulk bulk read and write operations are fast. That is the main objective. Okay, so Hive solves the problem of analysis on HDFS, and here it provides a SQL-like interface using which we can easily interact with the HDFS datasets, and we can perform any analysis. Okay. Any question so far? Any doubt, any concern? Any doubt or any question on Hive or how how we can know when to create bucket and partition. So yes, I explained this earlier as well. Uh, if we see that when there is the data uniqueness, what is uniqueness? So let's say you are storing an inventory database, okay? And now in the inventory, you have categories like mobile, sports, accessories. So these are categories. So create partitions. But in every category, now in case of mobile, we have a lot of companies, Sony, Ericsson. So that is buckets only. So here, let's say if we have 700 records and there are more than 100 departments. So better is to create buckets rather than partition. So it never happened that we have 100 departments, but if that happened, bucket is the best option to have. You understand? Understand this? Okay. So um, partition. So all this partition and bucketing, these are data organizing techniques. So we are organizing our data in different packets, you can say, small partitions. Okay. So that data scan is reduced. And I explained earlier that all the same column value will go to the same bucket. Okay. And we can use bucketing along with partitioning. That example we already seen. Partition is a directory and bucket is a file that we also see. And internally, bucket uses hashing algorithm to store its data. Okay. So here, bucket is a file, uh, and we can set the number of buckets during table creation. So in the script also we have seen that we have set the bucket number of buckets in during the data creation time. Okay, so that is regarding partitioning and bucketing. Now next is joins. So Hive supports all the normal joins like left join, right join, full outer join, inner join. All these joins Hive supports, but there are some special joins that we use in special scenarios. So let's say we have a large table that contains 10 billion records, and there's another table that contains 1000 records. So if we are joining these two tables, better is to use these special joins, map joins, bucket map join. If they are bucket tables, we use bucket map join. Normal Hive table, we use map join. So if we use these joins, our join performance is faster. So let's see how this performance is fast and how we implement these special joins in special scenarios. So let's check Hive map join. So there are two data sets. This is data set 1 and data set 2. First, load this data in the Hive table. This is a small table and this is a large table. It contains more records. Now, so first create table for data set 1. And this is the table for data set 2. Now load data in both the tables. Now this is the join query. So first remove this and for execute the query. Hive scripts. Where is map? This is Hive map join. Inside Hive map join. This one. So remove this final query, the join query, and just load the data first. So execute the query, the script. So Hive map join. Submit the script on the Hive server. Hive map join. Enter, and then it will load data from both the data sources into the Hive tables. So it's saying what happened? It's failed, invalid path. Okay, so change the data path from desktop and then inside desktop Hive script. Hive scripts, and inside Hive scripts we have dataset one, and change the path for this. Save this, and now submit this again. So data load is done. But now verify two tables. Select star from PVMS. Oh, sorry. Let's start from PVMS. Okay, so now these two tables are created on top, and if we see the script, now this is the join query. So first remove these. These are called you can say hint queries. So remove these hints and just execute the simple join query. This is the join query, and we are joining based on this condition. So this first name is common in both the tables. We are joining these two tables based on this column. So first execute this query. On Hive shell and see the execution time. And we can see that this job is also converted into MapReduce. So everything is converted into MapReduce because SDBus understand MapReduce only. So how much time takes 34 seconds for 20,000 rows. Now execute the hint query, or we can say the query, the map side join query. So copy and then execute and see how much time it will take. So 29 seconds. So this query is faster. This map side join query is faster than the normal join query. So we use normal joins when data is equal. Equal means let's say in one table you have 10,000, 10 billion, another table 8 billion, more or less same. But when there's a uneven difference, one table holds 1,000 records, another table holds millions record, then in case of those scenarios, we use map side joins on these spatial joins. So what happen internally? So see the join architecture, map side join architecture. So here we can see this one. If we see this diagram, so here we have a local task, a local mapper is launched. Okay. So if we see the logs, so let me submit this again. So whenever we submit a map join query, so this local task, local mapper. So this local mapper is launched. This mapper copy the data of small table into the cache, and this is Hadoop cache, HDFS cache, and this cache is maintained in master node. So if we saw this architecture, so here this is my name node, the master node. Okay, and these all are data nodes. Data node 1, data node 2, and data node 3. So on the name node is a master node. Here we will have the distributed cache. Distributed cache. So in this cache, your small table data is copied with the help of local mapper. Now what will happen during the runtime? When these mappers launch, these mappers are doing the actual comparison between these two tables. So these data automatically, data for the small table is available from the cache at the runtime. These mappers don't need to connect with the small table and retrieve data. If they retrieve the data again and again from this table, it will hamper the join performance. So in order to enhance the performance, we just this small table data is copied to the cache, and from the cache it will be available to the actual mappers before runtime. So if we can see here, this is the map join function, and in the map join function, we need to pass the small table only. If you pass the bigger table, it will throw out of memory exception because our cache memory is limited. Okay. So any question on this concept? This is very important. This is again optimization techniques when we are retrieving data from the HDFS, and as I said, all the data is stored in HDFS only. So if we see here in the warehouse, so warehouse you have these directories. So this is the table 1, and this is table 2, data set 2. Okay, so actual data is stored in warehouse only, but this interface is available to query the data that is stored within HDFS only. Any question so far? So I've covered partitioning. So I've covered Hive architecture and how we create table in Hive. What is the relation between Hive, HDFS, and what is metadata? What kind of data is stored in Hive metastore? And then I covered the optimization technique like this Hive partitioning and bucketing. That is during the data load. So whenever we are loading the data, we need to make sure that the data retrieval will be fast. So for that, we applied partition and bucketing. Okay. And then when we are retrieving data, whether from a partition table or a bucketing table or a normal Hive table, so we use these special joins, and these special joins again do the performance improvement. Any question? Any question, any query? No? Okay. So next, uh, so next is bucket map join. Next map is bucket map join. So bucket map join applies on bucket tables. So first, so because we are implementing bucketing partition, so we need to enable these properties. Now, this table is for data set 1. This is the bucket table. So here we will have 4 buckets. Now this is another table, has 8 buckets. So bucket map join is applied in the bucket tables, and when buckets are multiple of each other. So let's say here we have 4 buckets. So minimum 8 should be there. It can be 10 or 12 or whatever number, but at least the multiple of the smaller one. Then this join will show the performance improvement. So now we are then we insert the data into the bucket table. After inserting the data, now this property we need to enable for implementing bucket map join. In case of map join, we just add this property map join true. And now in case of bucket map, we use bucket map true. Just 1 minute. Okay, so first we create bucket tables. Then we insert data into the bucket table, and here we are implementing the map join, bucket map join. Map join function we need to use. This is the hint query, and let's execute this only. This one. This is sorted bucket map. So let's submit this. Oh, 1 minute. Open bucket map join and remove the SMB join script. So this is your map join script. I hope you guys understand. It just we create bucket tables only. The last time map join, we create normal Hive tables. So submit this script on the server. So Hive bucket map table. So now again, when we submit the script on the server, it's converted into MapReduce first. So it's right now it's loading the results, creating bucket table, then loading data, and then after loading data, then it will pull out the results. Okay, this is done. Now, let me check. 1 minute. First, check the tables. So, tables. Now, these bucket tables are created. Now, we can do our experiment. So, first, apply normal joins. 1 minute. Hive shell. The query. And we have removed those. Remove this hint. Now this is the query without bucket map join. This is a normal join operation. So now it's again converted into MapReduce, and the result is fetching 34.58 second, 20,000 rows. Now we use the hint query, or we can say the optimized query using bucket map join. So let's execute this and check this bucket map join. So again, a local task, local mapper is launched that copy that cache the results. And small table is always cache in memory. So then the actual mapper do the comparison between both the tables. So that data is available from the cache and your comparison will be faster. So 31 seconds. So it takes less time than the previous query. So that is the benefit of using these optimized joins instead of normal join. But we need to make sure that when there's a small and a large table, then only we use these joins. If data is more or less same, or approximately same in both the tables, then we go for normal joins one. Okay, so next join is sorted bucket map join. So in case of sorted bucket map, let me open the script. So this is SMB join here below. So in this SMB join, again, this is my table, first table. This is my second table. So data should be sorted, the join key. So first name is the common column in both the tables. So that key, or you can say the column, should be sorted. So here we are loading data in this table, but this time after sorting first name, then we load. So now this join is same, but here we need to enable this property sort merge bucket map true. Then only it will implement sorted bucket map join. Okay, so let's implement this. Mm, Link, okay. Mhm. So where is the script? Sorted bucket map join. This is high bucket map join. Let's transfer that file first. So your host is it's 128. Whatever. Whatever. So from here we can file scripts. Let's copy this. So it's copied. Now uh, check the script. I have bucket plan. So let's go to cloud. Where is high bucket man? This one, open. Now this is for the assembly join. Create one separate script for it. Um, Create a separate script. smb.hq. Take this file and now execute. So So we'll go to file, directory, and here we have assembly. Where is assembly? No, that is outside. Okay. your script is here. Now submit the script on the server. And see how assembly join is implemented. So again, this is converted into MapReduce. So job is running, okay, and it start a local task, local mapper. So local mapper always cache the small table data in memory. And now here we can see it's fetch 20,000 records in 31 seconds. Okay, so that is for the joins. So what we have studied so far, we have studied the Hive, how we create Hive tables, and then the various optimization techniques we have in Hive. Now, next, after these optimized joins, then we can create views in Hive. So why we create views? Any idea why we create views? Advantage of views, why we create views on top of table? So if we can see, so if this is the actual table, okay. So if we expose this table directly to the client, so we expose the data, some meaningful, you can say secure data. So instead, we create a view on top of this table so that we can share the columns or the data that is required by the client, not the other data that is sensitive. That's the main advantage of using Hive, and we can create Hive in a similar way that we create in SQL database. So Hive uses these support views as well. Okay, but main is the Hive. What is the purpose of Hive in big data ecosystem that I already explained? So if we see this architecture again, so now we can understand these points better. So MetaStore is the central repository. So metadata is here. This one, scope is the metadata, and it keeps all the metadata information related to all the Hive tables. Okay, and we usually store metadata in RDBMS source, and here in our case, our RDBMS source is MySQL. We can store in Oracle, Postgre, in other databases as well. And when we install Hive, at the installation time, we decide where we keep our metadata information. So let me show you in Cloudera. So Hive is actually stored here. Um, Hive. Uh, this is Hive. So this is where Hive is placed. So now if we see the scripts, so these scripts are provided by Hive community. So here inside this we can see Postgre, Oracle, MySQL, MS SQL. So we can choose any database for the metadata purpose. And these scripts, SQL scripts, are provided by Hive. So when we install Hive, so that time these scripts are executed, and these the tables that we are seeing here, these tables all are created with those scripts, and the schema is provided by Hive community. So they have provided these scripts along with the tool, so that when we install Hive on any of the environment, so we can create this Hive metadata. And these metadata tables, again, I said, it's for the data information, data about data. So it's keep the metadata information in these tables. Okay. So here, so as we can see here, this is our Derby. Derby is the memory database. We never store data in a memory database, because if we have multiple jobs running, so it's not able to append the metadata for both the jobs. So we normally use local metastore or remote metastore. In remote metastore, our metadata is stored outside of the Hive instance. Okay, the data types. So these data types we create when we create the table schema. The standard data types we'll cover tomorrow. So, and in the next class, what I will cover. So I will cover next window functions in Hive. That is the transformation functions. Window functions in Hive. So in window functions, ranking function. Ranking functions I will cover. And in the ranking function, we have rank, dense rank, row num. These all are, there are many others, but these are the ranking functions. Now, analytical function. Analytical functions like cumulative distribution, mean function. So these kind of functions are available. Then the aggregate function. Now, in case of aggregate function, sum, average, min, max, sum, average, all these are aggregate function. In analytical function, we also have lead, lag, percentile. So these all are the window functions. So I will explain how we implement window functions and in which scenario we use window functions. Then we'll cover Hive file formats. So Hive supports all the major file formats like Avro, Parquet, ORC. Then after that, we'll cover how we load XML and JSON dataset. You can say nested dataset, loading nested datasets in Hive. Example is XML and JSON. Then we'll see how we create custom schema in Hive. Okay. After that, uh, we'll cover Hive integration, how we integrate Hive with other with NoSQL databases like HBase, Cassandra. Okay. HBase, Cassandra, Mongo. So after covering all this, we will see. Yeah, these are the only topics. So the incremental load, how we load incremental data in Hive tables. That part also will cover. But these are the main topics we have in Hive. And after studying all this, we understand that Hive is a analytical tool, and we can see it provide functions, all the analytical functions. Now this tool is based on SQL language. Now similar stuff we need to cover in Spark as well. So Spark is faster. Hive internal engine is MapReduce only. So Spark process data in memory, and data processing is fast if in memory. In disk, data processing is slow. So Hive uses MapReduce as the internal engine. So we can say your Hive execution is slower than the Spark. But the concepts wise, the same topics we need to cover in Spark using Python, Scala, because it provide other APIs. Okay. So any question so far on today's session? Any question, any query? Anyone is having any question? No? So your environment is installed or still pending, Cloudera? Have you received the content that I'm sharing every day? Still pending. The installation is pending. So what happened? You're you're not getting the software, or what exactly? If you can share your screen, I can help. No, time. So, so yeah, I can solve cannot solve this. Need to bear your time and practice. So if you are facing any technical issue, I can help. Okay. So I will share these HQL scripts that I have executed today. So let's practice that. And if you guys face any issue, do let me know. We'll discuss tomorrow. Okay. And there are few other topics I forgot to mention. We have Hive UDF. Hive UDF, I forgot. And also have internal and external table concept. Internal and external table. So do we install MongoDB? Why? Why you are installing MongoDB? We are learning Hive. Install Hive first. Install Hadoop, install Hive, install Scoop. and practice. And then when we integrate Hive with any NoSQL engine, whether it's Mongo or HBase or Cassandra, then then we can install. But understand the concept. Don't go with these installations. You have enough installation. Cloudera covered everything. Why you are wasting your time? If you have environment available, so let's practice what I'm doing from last 4 class. I'm implementing all the concept, and you see I have mentioned everything here. Just practice these topics. This is enough to understand this ecosystem. And I have implemented these topics one by one practically. Understand? Okay. Okay, so that's it for today. Amar, do you have anything to discuss, or we
No,
can?
nothing. So, dear participant, I shared the attendance link. So, please mark your attendance.
Okay, thanks everyone. See you tomorrow then. Thanks, bye.